Good morning to all. We are discussing the automata in theory of computation. So in the previous lecture, we have discussed the finite automata, the concept of finite automata, the applications of finite automata where the automata is used, and the example how to design an automata for any problem, whether it is a real world problem or what any kind of problem is there. We can have the design, or we can design the automata for that particular problem. So the basic how to define the automata. So already yesterday's lecture we have seen the definition. The automata defined with the help of a tuple q, sigma, delta, q0 and f, whereas capital Q is nothing but the finite number of set of states. Then sigma is nothing but the finite set of input alphabets. Delta is nothing but your transitions from one state to the next state. Q0 is nothing but the start state, and F is nothing but your final state. In today's lecture, we are now moving further. As you know that this finite automata is divided into two types. That is nothing but the deterministic finite automata and non-deterministic finite automata. That is nothing but DFA and NFA. So in today's lecture, we are going to discuss DFA, that is nothing but the deterministic finite automata, the definition of DFA, and how to construct DFA for a given problem. Right? How to construct the DFA model for the given problem statement, that we are going to discuss in the today's lecture. So let us see the definition of DFA. So definition of DFA meaning is that it says that a finite automata is called deterministic. A finite automata is called deterministic if from every vertex of its transition graph, see carefully, from every vertex of its transition graph, there is an unique input symbol. There is an unique input symbol which takes the vertex state to the required next state. Means from each and every state, and on each and every input, there must be unique transition. Right? The word deterministic refers to the fact that the transition is deterministic. Means you can determine, for example, if there is a state Q0 and there are two inputs, that is nothing but two input alphabet A and B. So there is only one transition on input A from state Q0, and there is only one transition on input B from state Q0. There are no multiple transition on a single input alphabet. That's why it is called as the deterministic finite automata, or it is called as the DFA, right? So there is only one state to which an automata can transit from current state on each input symbol. So it is very simple. Just remember this thing, from only one state to which an automata, because there is only one transition from current input, and that transition lead to only one state. So there is not a case that from Q0 on input A, the two states are not possible. That is the case of your non-deterministic automata, right? So we are discussing the deterministic. Only one input goes to lead to only one next state, right? See here, so from state Q0, input A, from state Q0 for input A, only one path is going to Q2. From state Q0 on input A, this is the state Q0, input symbol is A, only one path, only one transition is going to state Q2, right? Similarly, from state Q0, there is only one path for input B, that is going to Q1 state. Getting this point? So if we consider that Q0 is the current state, and there are how many input alphabets are there? There are only two input alphabet, that is A and B. So input alphabet A leads to only one next state, and input alphabet B leads to only one next state, that is Q1. And these two states, that is Q1 and Q2, they are different, they are not same, right? So this transition, say for example Q0 on A, for example, there must not be any transition like this. Q0 on A leads to Q3. So on multiple transition on a same input symbol is not possible, right? So this is the case of your NFA, that is non-deterministic finite automata. But in case of DFA, only one input symbol, only one transition leads to the next state only, right? So there are two input alphabets, so definitely from Q0, one input leads to Q2 and another input leads to Q1. Getting this point? So deterministic, that's why it is called as a deterministic. Means yes, you can easily determine in the sense you can find out on Q0 input A go to state Q2 and Q0 input B go to Q1. There are no multiple states. Q0 on A it does not go to Q3 or Q4 like that. That's why it is called as a deterministic, right? So no state exists from which there are more than one transitions on the same input symbol. Just now I have said that there are no state exists from which there are more than one transitions on the same input symbol. That is the case of your NFA. We are also going to discuss after this a DFA, that is non-deterministic finite automata, where the multiple transition on same input symbol is possible, right? That means unique transition on same input symbol. So DFA, it is known for the unique transition on same or one input symbol only, right? So getting this point, so Q0 on A go to Q2, Q0 on B go to Q1 only, because there are only two input alphabet and they lead to specific next state, next state, or only single next state. There are no multiple next states on a single or same input symbol. So we'll see how to design a DFA. We'll see example. Suppose if there is a question to design a DFA, then what are the important or which are the different important points here? Suppose, so while designing a DFA, which things we have to consider here? So following four issues or following four important points that need to be considered. Number of states. First, we have to find out the number of states. Suppose a problem is given, design a DFA, just like here, design a DFA over input 0, 1. Input symbol 0, 1 means there are only two input alphabet 0, 1 to check whether a binary number has even numbers of 1. Suppose any binary number is given. Say for example 111100 or 0101. If this binary number is given and it is asked to design a DFA to check even number of ones, right? So in that case, what we have to do here? So first step is to find out or to identify number of states. First step is to identify the number of states. Second step is nothing but the transition function. Means how the transition takes place. Here it is very careful. So it is very important. You note it carefully. These are the four important points, that is start state and the final state. While designing any DFA, these 4 points need to be considered. First, we have to identify how many number of states it requires. Then suppose it requires 3 states or 4 states. Now, if there are 4 states, then how transitions will be there, or how the transition will occur in these 4 states, and which will be the start state and which will be the final state, that we have to identify. To design any DFA, to design any deterministic finite automata, these things first be identified. So let us see this example. Define or design a DFA over input alphabet 0, 1 that check whether a binary number has even number of ones. So see the states. First we have to find out the number of states. So we first find out the number of states. So there are only 2 states are possible, that is Q0. So Q0 state indicating even number of 1. So we will define a state Q0 that indicate only even number of 1. Suppose you take any number, say for example 10. Suppose this is the 10 is the number, and we have to find out how many even number of ones are there. So I can have defined Q0 indicating even number of ones, whereas Q1 that indicates odd number of ones. So 2 states are possible for this. And inputs, so how many inputs are there? So there are inputs 0, as next input will have no effect on number of ones. Input 0, yes, because we have only 2 input symbols 0 and 1, and input 1 as next input will make the transition from Q0 to Q1 and from Q1 to Q0. Means if there is a 0, if input is 0, definitely there have no, you do not have to change the state. So see here, read it carefully, as next input will have no effect on number of ones, because it is a 0, and we have to find out what we have to find out. We have to find out the even number of ones only. So if 0 is there, there is no state change. But if there is 1, so in simple word, we can say that if the input is 1, so input 1, there is a transition from Q0 to Q1. And if you are at state Q1, or if the machine is at state Q1 and 1 is found, then it will move to Q0, right? If the machine or if the automata is at Q0 and input 1 is found here, if the string is like this, 1 0 1 0. So like this, for example, suppose 0 1 0 1 0 1. If this is the string, so and the finite automata, you know that the finite automata start reading the string from the left hand side direction, and it will move toward the this particular direction. And if the input symbol is 0, so what we have to action we have to take here, we have no effect, because what we have to find here, we have to find the even number of ones, right? So suppose this is the string 0 1 0 1 0 1. This is the string. So in that particular string, if zero occurs, do not change the state. But if the one occurs, so for example, this is the one symbol, right? This is the one symbol, and this is the one symbol. So if you are at Q0 state, go to Q1 state. And if you are Q1 state, if one is the input symbol, go to Q0 state. Getting this point? So this is the way, right? Now the two step we have completed. We have identified the number of states. Which are the states are there? So these are the state Q0 and Q1. Q0 is indicating even number of ones, and Q1 indicating the odd number of ones, right? And inputs are 0. If 0 is there, no state change. But if 1 is there, you have to change the state, right? So these are the transitions then. So delta, you know that transitions are defined by delta functions. So the Q0 on 0, it will go to Q0 on 0, it will go to Q0, because 0 is the input and Q0, so there is no state change. So if you have, so we can say that Q0 on 0, Q0 on 0, there is a no state change. So there definitely there is a Q0. Q0 on 1. Now input is 1, definitely you have to go to Q1 state, right? Now delta transition on Q1 state, input is 0, you know, so this is the input symbol. So this, so you know that in case of delta function transition, this is nothing but your current state, and this is nothing but your input you are applying here. So I can have here input, and this is your current state, right? And you are getting here, that is nothing but your next state. Getting this point? So current state and next state you are getting with the help of this. So if the current state is Q0, input is 0, applied 0 to the Q0 state, the next state is also Q0. You are not going to change the state. Current state is Q0, the input is 1, you are going to change the state to Q1, right? The current state is Q1 now. Current state is Q1, input is 0, input applied to 0, the next state is Q1, right? And if the Q1 is the current state and input is 1, definitely, so here is no state change, but in this case, the state changes from Q1 to Q0, so that is the case. Here there is no state change, Q1 remains as it is. Here Q0, the state changes there, Q0 changes to Q1, and Q0 goes to Q0 here, right? So always in case of your DFA or in case of your finite automata, what you have to remember, you have to remember that, so what is the definition for delta transition? Delta is nothing but Q into sigma, that gives you Q. So this equation you have to always remember in case of your DFA, in case of your DFA, or in case of your NFA also. That means what we have to do here, Q into sigma means current state into input, that gives you the next state, right? So this is nothing but your, this is your one can say this is your transition graph, and the finally your the automata is like this. So this is your, one can say, the transition diagram. So this one is called as the transition table. So we have drawn the transition table for this. So this is your transition table. So this indicates your states, and this indicates your input alphabet, right? So Q0, see here, so this transition table, so this is same, this particular thing, it is same. So Q0 on 0, see here, it is the same. So you can write the transition like this, or you can have the transition table. These were and the same. So Q0 on 0. So how to read the transition table? Q0 on 0. So Q0 on 0, go to Q1. Q0 on 1, go to Q0 on 0, go to Q0. Q0 on 1, go to Q1. So this is the first, this is the second. Now Q1, see how to read the transition table. Q1, the current state is Q1, and the input is 0. Q1 and input is 0. Q1 and input is 0 mean this, and next state is Q1 itself. So again, it will come here, right? Current state is Q0. Current state is Q0. Now you are applying input 1, and the next state is Q0. You are getting next state is Q0. So that's why I'm saying that these transitions, they are very similar to your transition table. So you can have the transition table, or you can have the transitions delta. Delta means current state, Applying after applying input, you are getting the next state, or right. And after once you clear all these things, then easily you can have the transition diagram. You can have the transition diagram. And so this transition diagram, we can call this transition diagram, it is nothing but your require DFA. So this DFA gives you, or it will find out, you input any string. So you take any string, suppose 000, sorry, 110011. Suppose this input string is given to this DFA, so it will give you, or it will find out even number of ones. So meaning is that it will not give you any count ki how many even number of ones are there. It will not going to give any output, but it will only accept. It will only accept, or it will only reject, right? So means we have designed this particular DFA to accept the string, where the strings contain even number of ones only. This DFA, this finite automata, they are not going to give any sort of output to you, right? We are just only getting yes or no format output. Yes, yeah, whether this particular automata accept the string having even number of ones, yes or no. This sort of output, this sort of not output, but this sort of answers we are getting here, because this DFA, NFA, the finite automata, it is not designed for producing any kind of output. The finite automata with output, they are different machines. They are called as the Mealy machines and Moore machine, that we are going to discuss later on, right? But for the timing, just remember here, this transition diagram, it is nothing but your DFA. It is not going to produce any output, but it only check the string, whether the string is being accepted or not. So when the string will be accepted, when this particular DFA, you are entering the string having even number of ones, then and then only the string will get accepted. If there are no even number of one, so the string will be rejected. Getting this point? So this is the way how to design the DFA. So first we have to find out the states. So first we have to find out the state. This is the first. Then we have to find out the transitions, how the transitions will take place. Then we have to find out the start state, and then we have to find out the final state, right? So these four states we have to consider here, right? Okay, next we'll see another example, example number 2. So design a DFA over input. Now here input alphabets are A and B. Only two input alphabets are there, A and B, to check whether a string over alphabets contains a substring A, B, B. Means substring means what? Substring. So first define the substring. Substring in the sense, it is nothing but the part of a string. So consider any string. Suppose I draw here. Suppose A, B, A, B, A, B, B. So this particular string contains a substring A, B, B. This is a string, total string, and this string, the ABB is a part of this main string. Or I can have AB, then ABB, AB. Right? So this, there is a substring. So meaning is that it contains the substring ABB. Meaning is that the arrangement of letters must be in this format ABB. Means there must be first A, then there must be B, and there must be B. So if three letters are consecutive to each other, then we can say that yes, this is nothing but the substring is there. So I can have any sequence. So I can have double B, then ABB, then I can have double A. But here this substring is there. So the meaning is that, so first understand the question. So I have to design a DFA in a such a way that if I input a string, any string having substring ABB, then that particular string is being accepted. Getting my point or not? Suppose if I enter this particular string to my automata, this string must get accepted by the automata because it contains the string ABB, right? But if the string does not contain the substring ABB, then that particular string get rejected by that particular automata. So I have to design a automata, DFA, deterministic finite automata, in a such a way that it must accept the string, or it must accept the strings containing the substring ABB. Okay, so we'll see the steps, right? The states, first we have to define the states: Q1, Q2, Q3, and Q0, right? So Q1. So Q1 in the sense it preceding symbol is A. So all its preceding symbol, all the previous symbols must be A. Then Q2, the state defined here, preceding symbol means whatever may be the symbols received at the Q2 end, they all contain AB. And Q3 means all symbols ABB, means it is the state where all symbol it received, that is nothing but ABB substring it received at Q3 end. And Q0, so rest of all the conditions, means rest of excluding all these three conditions, whatever may be the situations are there, these are handled by your Q0 state. Right? So meaning is that we have to consider, so there is a Q0 state and Q0, so this is the, say for example, your Q0, and if it gives A, so there must be Q1 state, right? So here you are reading A here, right? Then from, so on Q2, what is the definition of Q2? The preceding symbol is AB, means suppose I draw here B, suppose Q1 and on input B, so definitely it is going to Q2. So here, how much string you have read here? I have read up to AB, 2 letters of the strings I have read here. And finally, so this Q3 tells that Q3 is nothing but your ABB. So definitely ABB. So this at Q3, at end of Q3, I must able to read ABB string. Getting my point or not? How I am going to define the states. So be very careful while defining the states. And then you have to define the transitions. And there are how many inputs? So on each state, here on each state, suppose Q0 is there, so for each state A transition must be there and B transition must be there. Suppose any state, you take any state, suppose Q1 is the state, there must be transition on input A and there must be transition on input B. Remember this point always, right? Always remember this point. So inputs are, so if there are four states, and there are two inputs, then their total transitions, how much will be the transitions? So 2 into 4, that means there must be total 8 transitions are there. Getting my point or not? If there are four, because each state must be transist on each input, right? So multiple, so there must be multiplication. If number of states are 4, number of inputs are 2, definitely how many transitions are possible? Total 8 transitions are possible. Remember this point always. So next point or the next step is, see here. So transitions are, see. So I have taken Q0, right? So Q0, the first state input is B, it will go to Q0 state, right? And if the input is A, then it will go to Q1 state. Getting my point or not? So each on single state, Q0 state, there are two input transition, one transition on input B and another transition on input A. On input A, it go to next state, that is nothing but Q1. But on input B, it will be self transition. Right? Q1 on A, it is a self transition, because Q1 on A, it will not go to next state, but Q1 on B input, it will go to Q2 state. It will definitely go to Q2 state, right? Then Q2 on A and Q2 on B. So on Q2 state, on transition A, it will go to Q1 state. See here, and Q2 on B, it will go to Q3 state, right? So and Q3 on A remains at Q3 and Q3 on B remains at Q3 only, right? So there is a no state transition on input A and on input B for Q3 state. So the next state is Q3 itself. So see here, the from this particular, one can say the from these transitions we have drawn here the transition table. It is called as the TT or the transition table. See the same. So you can have this Q0B. So Q0 on B go to state Q0 itself. Q0 on A go to state Q1 itself. Here is a 1, right? Then Q1 on A go to Q1 and Q1 on B go to Q2 state, right? Then Q2 on A go to Q1, Q2 on B go to Q3. So Q2 on A go to Q1, Q2 on B go to Q3, and Q3 on A remains at Q3 and Q3 state on B input remains at Q3 state only. Getting this point? So, and one important point here you have to note here, the star is marked here. So you can either mark star here or you can mark star here. So star indicate this Q3 is the final state. So remember this point, various concept which you require throughout the subjects that I am discussing here. When it is a, suppose it is like this Q3. So this indicates, star indicated, it is the final state. And in case of while drawing the transition table, in transition table you can mark star, identify the final state, and you can mark arrow here. That arrow indicate your start state. That means if the state is like this, suppose q1, so I can say that q1 is the start state for your understanding, right? In case of your while marking the transition table. And finally, we can have the DFA drawn like this, right? So see here carefully how the DFA is draw. So what we have to find here, we have to draw the DFA. We have to draw the DFA to find out, to accept the string having substring A B B. So already we have drawn that. Suppose this is the Q0. So on A input it will go to Q1 state, and on B it will go to Q2 state. So here A is seen. So first A of the substring is seen here. So so that is here. At Q2 you are seeing AB. AB is seen here. So AB you can able to see here. And at Q3, so it is as it is a final state. And while drawing the transition diagram, also remember, while drawing the transition diagram, the final state, as you know, that it must be marked with a double circle, and start state with mark with this arrow. So this arrow indicates it is the starting of the transition diagram, and if this double circle and Q3 is there, it is nothing but your final state. So here I can able to visualize ABB is seen. ABB is seen here, right? Getting my point or not? So this is nothing but the automata. This is nothing but the simple automata where I can have the substring that is A, B, B. It is seen here. Getting my point? Now the question is in your mind that how many transitions we have drawn here? We have drawn here only 1, 2, 3 transitions. We have drawn only 3 transitions. And how many total transitions are there? 1, 2, 3, 4, 5, 6, 7, 8. So out of 8 transitions, how many transitions we have drawn here? We have drawn only 3 transitions. So remaining 5 transitions we have to draw. So always draw the graph or the transition diagram like this. First draw the diagram for the string which is being asked. The string which is being asked, that is ABB is being asked. So first draw for ABB. And now rest of the transition. Now see carefully, Q0. Now consider the state Q0. Now Q0 on A, it will go to Q1. Now what about next input? So you have to think of Q0 on B. So definitely Q0 on B, it will go to Q0 on B, it must go to Q0 state. So it is nothing but the self transition, that is nothing but B. Right? So 2 transitions or all the transition on this state Q0 is completed. On one input it will go to Q1, and another input it will be the self transition. So this is the thing, while drawing the diagram, transition graph, you have to see that each state must have the transition on each input symbol. So how many input? 2 input symbol and 4 states. There must be total 4 into 2, total 8 transitions are there. So this is the method how we are going to draw the DFA, deterministic finite automata. Right? Now go to A. Now A has transited from B input B. Now means one input it has there is a transition on B. Now what about A? So A, that is nothing but the transition Q1 on A. Q1 on A go to Q1 itself. So this is again a self transition A. Q1 on A is nothing but the self transition here. Right? Now Q2, one transition is completed on B. What about A? So here to draw this A. See here. See, it is very important. Suppose if I draw A here, if I take the self loop A here, then what will be the string? So string sequence get disturbed. Why? See here, you will get here B and you will get here A. So instead of A B, you are finding here, you are getting here A B A. You are getting here A B A, which we don't require. Getting this point? So very important, where to transfer this A. So that's why this is wrong. So do not get the self loop, or do not take the self loop for A input. So where to transfer it? So definitely I can transfer to here A. Right? So though there is a, so what will happen here? A B. So definitely again I am getting the same string, that is nothing but AB. Getting it or not? So this is the point how we have to what we have to think while drawing the DFA. This is the important point. This is very important, right? Now for Q3. So for Q3, so any transition, so all the transition you can have A or you can have B. It can be a self transition. Why? Because it does not going to disturb your substring. Why? What happened? Because you, at Q3 already ABB is seen. At Q3 already ABB is seen. So though if it is A, so ABB and finally it is A. Suppose if it is A, and if it is a B, so ABB is there and you are getting here B, but your substring is not getting disturbed. Getting my point or not? But in case of Q2, if in case of Q2, if you terminate the self loop here or if you draw the self A loop here, so it will definitely going to disturb because it will becomes A, B and A. So your ABB sequence get disturbed here, right? So instead of this one, you have to go to this one. So it becomes A, then again B, B. So your this particular sequence will not going to disturb here. So this is very important. Carefully observe this while drawing. So all your 8 transition 1, 2, 3, 4, 5, 6, 7 and 8, all 8 transitions are completely done here, right? So this is the way how to draw the deterministic finite automata. Getting this point? Okay. Well, okay, we'll see some examples on DFA. There are examples which makes more clarity, which brings more clarity in your how to draw the DFA, how to draw the transition graph for this, right? So see here, design a finite automata which accepts the only input 101 over a input alphabet 0, 1. So the question is like, so you have to draw, the finite automata that is definitely deterministic finite automata, right? That accepts the input string that is 101 and over the input symbol 0, 1. Over the input symbol that is nothing but your 0, 1. So what I draw here, so just so how to draw this? The steps are like this. Say for example, start drawing very simple Q0 and what is the string? The input string is 101. So I can have 1. So Q1 on 1, very simple. Okay, Q1, sorry, Q0 on Q1, then on Q2, right? On 0 and on finally on Q3. And Q3 make this Q3 as a final state. So I get this 101. Is it clear to you? So how to draw this? It is very simple. There is a one can say that there is no such a mathematics or any rules or regulations or any norms are involved here. It is very simple. It just logic is involved. You have to apply your logic here. So 0, 1, 0. What is asked? So 101 is asked here. So 101 I can draw Q0 on 1 go to Q1. Q1 on 0 input go to Q2. Q2 on 1 go to Q3. It is very simple, right? So at Q0 1 is seen. So here it is marked here 1 is seen. At Q2 10 is seen here, right? And at Q3 101 is seen. Clear? Okay. Now how so rest of the transition, rest of the how many states are there? 1 to 4 states are there. 4 into inputs alphabets are 2. So definitely total transitions are 8. Now mark the remaining transition. Now start marking the remaining transition. Now how to mark the remaining transition? So see here Q0 on 1 you have already marked. So 1 input. So how many inputs are 0 and 1? So each state must have transition on each input. So Q0 on 1 is already done here. Now what about Q0 on 0? You have to mark Q0 on 0. So Q0 on 0 you can mark it on self loop because why? Because you do not have to disturb, you don't have to disturb this 101 sequence. This sequence must be maintained. That's why Q0 on 0 it is nothing but your self loop. Getting this point? Okay, so all these two inputs are over for Q0. Now come to Q1 here. Now to come to Q1. Q1 on 0 is already completed. Now only 1 is remaining. Only 1 is remaining, right? So where to mark Q1? Where mark Q1, right? So Q1 on 1, it is marked here self loop. And markings here self loop, it is not going to disturb. It will not going to disturb your string. See here, if I mark here, so I'll get here 101. This one, this 0 and 1. So the string which I require here, it will not going to disturb. That's why Q1 on 1 self loop mark, it is also okay. There is no problem while marking the self loop for input 1. Right? So question about Q1 on both inputs are okay or over here. Now come to state Q2. Come to state Q2. So Q2 on 1 is done. Q2 on 1 is done. Q2 on 0 is remaining. Q2 on 0 is remaining. So where to transfer this Q2? So shall I mark here on 0? So if I mark here 0, so what? So how the sequence becomes 0, 0, 1, 0, 0, 1, which I don't require. So that's why I told that you have to apply your mind, you have to apply your logic. So if I mark here self loop, so the sequence of the string becomes 0, 0, 1. But we require 0, 1, 0. This particular string or this particular sequence must not get disturbed. At the end, at Q3, there must be 1, 0, 1. It must get seen here. Getting my point or not? That's why what we have to do here. So instead of marking here, so 0, 0 must be transferred. 0 must be transferred here. Right? So by transferring 0 here, it will not going to disturb, it will not going to disturb your sequence. Getting this point? So this is the way, right? So it will become 1, 0, it will become 1, 0, 1 again, right? And on Q3, now come to Q3, Q3, so 1 and 0, so both inputs. So Q3, there is no transition on 0 as well as no transition on 1. So where to transfer? So shall I make it on here? So no, I cannot make it on a self loop. I will transfer these both inputs on Q1 or Q0, that is nothing but 1 and 0. So that at the end, I must able to see 101 as the string. Getting this point? Okay, so it is very simple. There is no any mathematics, nothing is involved, only logical. It is the total subject is purely logical. You have to apply your logic or you have to apply your mind, right? So next example, design a finite automata which accepts only those strings which starts with here, 1 and ends with 0. Means which strings, say for example 0, 1. This is one string that starts with 1 and ends with 0. So I have to design such an automata. It will take, so if I enter this string, it will accept. If this is the string 1, 0, 1, 0, 1, 0, yes, it is accepted. Yes, accepted. But if the string is like this, 0, 1, 0, 1, 0, it will not going to accept because it does not start with 0. But though it ends with 0, but it does not start with 1. Right? So I have to design an automata for the string. So it may be string. So string may have any length. String maybe have any length. Say for example 0, 0, 1, 1, 1, 1, 0, 0, 0. So this string is there. That particular string starts with 1 and ends with 0. So I have to design an automata for such a string that must start with 1 and ends with 0. So the steps. Very simple. This is the very simple. So how to draw this or how I can start drawing this? So first step, just see here, first step I can draw here. So I can have the Q0. Very simple, just how to draw Q0. The starts with 1, just starts with 0. So what is the basic, which is the minimum string for this? The minimum string for this is nothing but 0, 1, 0. Starts with 1 and ends with 0. So 1, so design for this Q0. On 1 go to Q1 and Q1 on 0 go to Q2 and make this Q2 as a final state. Simple. Okay, so this is your automata. This is your finite DFA, deterministic finite automata, that accept the strings and make it as a start state. Q0 on 1 go to Q1, Q1 on 0 go to Q2. This is the thing only, right? Now, so how many states are there? There are 1, 2, 3 states are there. And how many inputs are there? There are 2 inputs. So how many transitions must be possible? The total 6 transitions are there, right? So 6 transitions means remaining transitions. So Q0, right? Q0 on 0. Where to transfer that Q0 on 0, right? So Q0 on 0, I can transfer here. So here I cannot have the Q0 on 0 because if I make it here, so the string will start with 0. If I give it a self loop, so the string will start with 0. So instead of here, so I can go to the here 0, right? Or I cannot mark. So instead of this, I cannot mark. So I can have Q0 on 1. It will go to Q1, but on Q0 on 0, it will not go to any state. So I can make it as an empty transition. So there will be no transition on 0 input. because it will not be accepted. It will not be accepted at all. Getting this point or not? Because you need a string that must starts with 1, and if the string starts with 0, so there is no need to go further. Getting my point or not? There is no need to proceed further in reading the input string. So q0 on 0, that's why it is not marked here in this diagram, right? Now q1. Now suppose at q1 0 is encountered, definitely you have to go to the next step, that is nothing but the q2. But if that q1, if the 1 is encountered, so 1 is marked as a self loop here. So 1 is marked as a self loop, right? Now at q2, so at q2, if the 0 is input, so 0 is marked as a self loop, because no doubt the string must be end with, 0. But if 1 is there, so I have to mark the transition to q1. Right, so if I read the string, so 1 and 0, that sequence must not get disturbed. My sequence is 1 and 0, this sequence must not get disturbed. Getting this point? Getting this point or not? So this is the way how to draw the DFA. So this is the correct DFA drawn here. So you have to see here, so q0, only one transition is possible. On 0, there is no transition is taken here, because if you are taking 0, then there is a total wrong. It will become total wrong here, right? So this is the way. We'll go to the next example. Design a finite automata to accept the string that always ends with 0, 0. That always ends with 0, 0. See here. Step 1. So already stepwise I have drawn here now. So simple automata. Q0 on 0. So we have to design an automata in such a way that it always ends with. So always remember what the question is asked. So try to understand the question first. It always ends with 0, 0. So very simple word, 0, q0 on 0, it will go to q1 after applying 0, it will go to. So here I see here 0, and here at the end of q2 I see 0, 0. So definitely whatever may be the strings you are going to input, that definitely ends with 0, 0. This is nothing but our step 1. The step 1 is nothing but how many transitions are there? Only 2 transitions are shown here. What about remaining transitions? Now what about the remaining transitions? So remaining transitions we have to say, because q0 on 0 is there, but what about 1? q0 on 1. So that we have to show here. Now q1 on 0 is shown here, but what about q1 on 1? That we have to transfer this. And q2, both the transitions on q2 on 0 and q2 on 1, that both transitions we have to mark here. So 1, 2, 3, 4 transitions are there that we have to mark here. How it is marked here? Step 2. Right? So q0 on 1, it is marked as a self transition, because what happened, you must not disturb this 0, 0 sequence. At here we must get here 0, and at q2 I must get here 0, 0, what it may be. So if I transfer this q0 on here, say for example, if this is the transition 1, so it will going to give you the 1, 0 string, but we don't want 1, 0 string, we want 0, 0 string. That's why q0 on 1 must be marked as a self loop. Getting this point? Right, so the 2 transitions are over for q0. Now for q1, the transitions 0 is there. What about 1? So 1 is now transferred to q2. After applying 1 as input, it will go to state q0. So see here, because we are not going to disturb this 0, 0. So see, read the string. This 1, 0, 0 means, if I read the string like this, 1, 0, 0 means I get here 1, 0, 0 means 0, 0 at the end. Getting this point or not? Then so both the transitions are over for q1. Now q2. Now 0 is marked as a self loop. 0 is marked as a self loop because what? So you take any, suppose this 0 and this 0, still you are getting 0, 0. Getting this point? But 1 is not marked as a self loop. 1 is not marked as a self loop. 1, you are taking this 1 to the q0 state. You are taking this 1 to the q0 state. Getting this point? So means what happened? So this 1. So see this 1, 0, 0. So you are getting this string like this 1, 0, 0. You cannot mark this 1 here itself also. So q2 on 1, if you can go to q1, so this will also going to disturb your string. You are getting the string like this 1, 0. This is also wrong. Getting the concept or not? If you try to put this 1 here, so the sequence you are getting here 1, 0, but we don't want this 1, 0. So that's why I put here the transition on 1 input from q2 state to q0 state and not q1 state. Getting this point? So why? Because our conditions are there. We want such a string that must end with 0 0. There must not be 1 0. There must not be 0 1 like this. We must be there. Must be 0 0. Two letters, two alphabets must be there. Consecutive 0 0. Right? Okay. Design a DFA, design a deterministic finite automata to accept the string in which A always appears triple. So there are means we have to design a automata where A, this letter, the arrangement of letter A must be like this, A. Means there is a substring, means if any string is there, suppose B, A, B. So this is the triple A must be there. So format of A must be in a triplet format, means it must be occurs in a triplet format. So if it is a BB, so there must be A, B. So this string must get accepted. But if it's a string like this, AB, so AB, this string is not getting accepted here because we want, or we have to design a DFA. We have to design a DFA in such a way that the A must occur in this fashion only. Remember, this is a formal language. This is a automata. We are designing automata for the formal language. We are focusing upon how the letters are arranged, their arrangement and not their meaning. Getting this point? We are arranging, we are focusing on the arrangement. So A is must, A arrangement of letters in this fashion. Their meaning, so what is the meaning, we are not focusing, right? So if this is a string, we have to design automata to accept this string, right? Then how to design? See here, step number 1, very simple step. Q0A go to Q1, Q1A go to Q2, Q2A go to Q3. Very simple, right? And then step number 2. So why step number 1 I have drawn here? Because what we have to do here, we have to just make a transition on triple A, means the whatever may be the asked in the question, that first you have to draw here. So yes, A transition. So here you are getting out, you are seeing the string A. Here also you are seeing double A, and at the end you are able to see the string as a triple A. Right now, the step two we are designing here, because whatever may be the remaining transitions, yes, because there are two input, there is not a single A, there are B, and here all the transitions are make on input A. So what about B transition? So we have to transfer that B transition to some state, right? So we have to transfer. So see here, step number 2. So all the B transfer are, so here, so Q0 on B transfer to self loop, or it is transferred to same state here. So I can say here how to write the delta function. Q0 on A go to Q1 state, Q0 on B go to Q0. It's getting this point or not? So delta function I can write like this: Q0 on A go to Q1, whereas Q0 on B only Q0 state is there because it is self loop, or it is a self transition. And it will not going to disturb your disturb your string. Why? Because you are getting the string like this, B, A, and our string remains as it is, right? Q1 already. So question about Q0, AB is over. Now come to the next step, that is Q1. Now Q1, A is the A completed on input A. What about B? So you cannot have B here. You cannot have B here. Why? Because if you put the self loop here, if you put a self loop, then the string sequence becomes like this. It becomes your AB here, right? And we don't want B in between A. Getting this point or not? So this will going to disturb your string sequence. We want 3 consecutive A's. That's why the B transition, it is put on Q0. It will go to Q0 state. Now what about Q2? Q2 is here, and same question, or the same thing is repeated here. If I put here B, so here what I get here, A, but we don't want B in between to A. That's why, so B is now transferred from Q2 to A. So on input B, the state Q2 goes to Q2. So delta function I can write like this: Q2 comma B, it is nothing but your Q0, and delta Q2 comma A, it will going to Q3 state, right? And what about Q3? Both input for A and B you are making as a self loop, because what happens once you get triple A as a sequence, then whatever it may be, so this B will become here, so B, So then it will not going to disturb your sequence, or suppose this A is there. So triple A, already triple A you got here, that is triple A, and this is the final A. Still your the sequence triple A is not getting disturbed here. So there is no question, there is a self loop. It will not going to disturb your triple A sequence. Getting this point? So if I have to write a delta function or the transition function, delta q3 comma A, that is equal to q3, and delta q3 comma B, that is equal to q3 again, right? So this is the way. And for this you can draw the transition table. Means you can have the this is the q, these are nothing but the states, q0, q1, q2, q3, and this is input alphabets are how many? A and B, A and B. So I can have q0 on A, q0 on A go to q1, and q0 on B go to q0 itself, q1 on A go to q2, but q1 on B go to q0. q2 state on A input, q2 state on A input go to q3, but q2 on B go to q0, and q3 on A go to q3 itself, and q3 on B go to q3 itself. So this is the transition table. This is the transition table. These are nothing but all the transitions. These are the transitions on each state, on each input, and this is nothing but your transition diagram. Transition diagram for the DFA, deterministic finite automata, right? So just go through it once again. There are few more examples that we will continue in the next lecture. Getting this point? So for today's lecture, we will stop here, and there are few examples still remaining that we cover in the next lecture.